Welcome everyone to Sham Discovers. Let's learn something new today. Welcome, future scientists and curious minds. Today, we're going on an incredible adventure to understand electricity, the invisible superpower that lights up our world. From tiny particles to giant power grids, we'll explore how it works and how we learn to harness its amazing power. Get ready to be enlightened. To understand electricity, we first need to zoom in, way in. Everything around us, from a giant tree to the smallest grain of sand, is made of tiny building blocks called atoms. Think of atoms as the Lego bricks of the universe, too small to see without special tools. Inside every atom are even smaller parts, protons, neutrons, and electrons. For electricity, the most important players are the electrons. Imagine them as tiny, energetic dancers constantly swirling around the center of the atom, eager to move and explore. You've probably already experienced electricity without even knowing it. Remember rubbing a balloon on your hair and making it stand up? That's static electricity at work. It happens when electrons jump from one object to another, creating a temporary imbalance. For electricity to flow, electrons need a path. Some materials, like metals, are excellent conductors. Think of them as superhighways for electrons. Their electrons can move freely from atom to atom, making it easy for electricity to travel through them. On the other hand, some materials are insulators, like rubber, plastic, or glass. Imagine these as roadblocks for electrons. Their electrons are tightly held and don't move easily, which is why we use them to cover wires and keep us safe from electric shocks. For electricity to do work, electrons need a complete, unbroken path called a circuit. Think of it like a racetrack where the electrons run in a continuous loop. If the track is broken, the race stops, and nothing happens. Where do electrons get their energy to move? From a power source. Batteries are like little electron pumps, using chemicals to push electrons through a circuit. They give electrons the oomph they need to start their journey. For bigger jobs, like powering a whole city, we use generators. These giant machines spin magnets near coils of wire, creating a powerful push that sends countless electrons flowing. Imagine a huge hamster wheel, but instead of a hamster, it's magnets spinning to create electricity. Now for some important terms. Voltage is like the push or pressure behind the electrons, determining how much force they have. Think of it like water pressure in a garden hose. High voltage means a strong push, while low voltage means a gentle flow. Current, measured in amperes, is how many electrons are actually flowing past a point in the circuit each second. Using our water hose analogy, current is like the amount of water flowing out of the hose. A wide-open hose has a high current, while a trickling hose has a low current. Resistance, measured in ohms, is anything that slows down the flow of electrons. Imagine a narrow, bumpy section in our garden hose. It makes it harder for the water to flow through. Wires can have resistance, and some components are designed to have high resistance to do specific jobs. So, what happens when electrons meet resistance? They get excited and release energy. In a light bulb, electrons push through a tiny, thin wire called a filament. This resistance makes the filament get so hot that it glows brightly, giving us light. That same resistance can also create heat. Think about your toaster or an electric heater. Electrons flowing through special wires with high resistance generate enough heat to toast your bread or warm your room. It's all about converting electrical energy into heat energy. Electricity can even make things move. Electric motors use electricity to create magnetic fields that push and pull, making parts spin. That's how electric fans cool us down, washing machines clean our clothes, and electric cars zoom down the road. Our journey through electricity's history begins thousands of years ago with the ancient Greeks. They noticed something peculiar about amber, a fossilized tree resin. When they rubbed it with fur, it attracted light objects like feathers, a very early encounter with static electricity. The Greek word for amber was elektron, which is where our word electricity comes from. For centuries, static electricity was mostly a curious parlor trick. People didn't yet understand the powerful force they were witnessing, just that it was fascinating. Fast forward to the 18th century, and meet Benjamin Franklin, a true American inventor and scientist. He wondered if lightning was a form of electricity. In a famous, dangerous experiment, he flew a kite during a thunderstorm to test his theory. Franklin's experiment, though risky, proved that lightning was indeed electricity. This discovery led him to invent the lightning rod, a metal pole that safely guides lightning into the ground. It protected countless buildings from fiery destruction, a brilliant application of his electrical knowledge. While Franklin explored static electricity, Alessandro Volta, an Italian scientist, was busy creating a continuous flow of electricity. In 1800, he invented the voltaic pile, the world's first true battery. This was a monumental leap, providing a steady, reliable source of electric current. Volta's battery wasn't just a curiosity, it was a game changer. Suddenly, scientists could experiment with a constant stream of electrons. This steady power allowed for countless new discoveries and laid the groundwork for all the electric devices we use today. Next, meet Michael Faraday, a brilliant British scientist who uncovered another incredible secret, the connection between electricity and magnetism. He discovered that moving a magnet near a coil of wire could generate an electric current. This was a huge breakthrough. Faraday's discovery led to the invention of the electric generator, which we talked about earlier. By spinning powerful magnets inside wire coils, we could create electricity on a much larger scale. This was the key to unlocking widespread electrical power for everyone. Now, imagine a world without electric light. In the late 1800s, Thomas Edison, the famous American inventor, changed that forever. After countless experiments, he created a practical, long-lasting incandescent light bulb. His invention truly brought light to the world. Edison also championed direct current, or DC, where electricity flows in one constant direction. He built power plants that supplied DC electricity to homes and businesses, but it had a limitation: DC couldn't travel very far without losing power. It was like a short-range sprint. But another brilliant inventor, Nikola Tesla, had a different idea: alternating current, or AC. With AC, the direction of the electron flow rapidly switches back and forth. Tesla's AC system was much more efficient for transmitting electricity over long distances. Edison and Tesla famously had a war of the currents, each believing their system was best. Ultimately, Tesla's AC system proved superior for widespread power distribution. It could be easily transformed to different voltages and sent across miles of wires to reach cities far away. Thanks to Tesla's AC, we now have vast power grids that deliver electricity to almost every home and building. Huge power lines crisscross the landscape, carrying electricity from power plants to distant towns and cities, lighting up our modern world. Today, electricity powers everything from our smallest smartwatches to giant supercomputers. We're constantly finding new ways to generate it, like solar and wind power, and new ways to use it. Electricity is truly the engine of our modern world. From ancient amber to global power grids, electricity has come a long, long way. It's an invisible force that continues to shape our lives and future. Keep exploring, keep questioning, and who knows, maybe you'll be the next great inventor to spark a new electrical revolution. Thank you for watching. Don't forget to subscribe to Sham Discovers and turn on the notification bell for more educational videos.